Here's a claim, evidence, reasoning question, for AP Physics 1. In this situation, we've got 3 different inclines. Everything is the same on all of the inclines except for the fact that the angle increases from A to B to C. We're supposed to explain our rationale between ranking the accelerations of the masses on the different inclines. So we're going to use our force toolkit. Our first question is, what is our accelerated system? It's the block. The coordinate system is along the incline in the positive direction. We'll say down in the direction of the moving block. The force diagram looks like that. The normal force perpendicular to the incline, the kinetic frictional force parallel to the incline, opposite the direction of motion, and the force due to gravity straight down. When we rotate the force diagram, it looks like that, so that the normal force is straight up. Then we have our equations for the force due to gravity in the parallel direction, that's Fg cosine theta. In the perpendicular direction, it's Fg sine theta. Then we substitute in the force due to gravity in each of them. The force due to gravity we know is mg, so those are the equations that we get. Then we look at the motion maps. The motion maps, if it's rotated, it accelerates to the right, the velocity increases to the right. If we don't rotate it, it increases down the incline. The velocity increases down the incline with a constant acceleration down the incline. Then we go to that step, Newton's second law. Then we write out the horizontal version of Newton's second law and the vertical version of Newton's second law, which depend upon our force diagram. Then we also know that this kinetic frictional force is equal to mu, the coefficient of friction, times the normal force. We plug in some of our values here in the vertical. We realize that there's no acceleration vertically. It's not moving in the vertical. In this direction, it's not moving. So the acceleration is 0. So therefore, we can just plug 0 into the vertical Newton's second law equation. And therefore, we'd have the normal force equal to mg cosine theta. Since the normal force is mg cosine theta, I can plug it into the kinetic frictional force for the normal force, and I get that equation right there. If I plug in my parallel equation from right here into there, I get this entire equation for the horizontal, and I can solve that for the acceleration. Now, if we look at the general case, the equation would look like this in general in all 3 situations. But if we look at it for each situation where we plug in the value of the angle, notice that everything is the same except for the angle. Okay. All right. And then if we look at the motion maps, look specifically at what's going on with the lengths of the parallel component. Notice the parallel component increases from A to B to C as the angle increases. Notice that the perpendicular component decreases as we go from A to B to C. That's important. Okay, so if we look at their specific equations, it would look like this. Okay, now let's get to the evidence part of this. So evidence is what physics information is given to us or easily inferred. Well, we know that the angle increases. That's given to us. They tell us that the mass remains the same. Where is that same object m? The contact surfaces between the incline and the mass is the same for all 3 situations. Therefore, the coefficient of friction remains the same. So these are all things that's given to us or stuff that's easily inferred. Okay, so then our reasoning. What are the important relationships that connect your evidence to your claim? So first of all, we got to use Newton's second law. That's the biggie here. That's our really big important topic. Newton's second law says the acceleration is proportional to the sum of the forces in the parallel direction. So my mass and my acceleration is equal to the sum of my forces in the parallel direction. So in all of them, the Fg parallel minus Fka, or Fk equals the mass times acceleration. So we're looking at 2 things specifically, the parallel direction, the force of the parallel direction, and the kinetic frictional force. First, let's focus on the parallel component of the force due to gravity. Since the mass remains the same, the force due to gravity stays the same for all three situations. So the force due to gravity there, and there is the same. The parallel component of the force due to gravity increases when the angle of the incline increases. So if you take this equation here, if we increase that angle, the sign of that angle causes the parallel component to increase from A to B to C. So if that's true, we could say, therefore, as the angle of the incline increases, the force due to gravity in the parallel direction increases. So these are three steps to say that FGA is less than FGB, which is less than FGC. So FGC has the highest parallel component of the force due to gravity. Now let's look at the other thing that affects the acceleration in the parallel direction. That's the kinetic frictional force. Okay, so that's that part right there. What we want to say here is a perpendicular component of the force due to gravity decreases when the angle of the incline increases. So this FG perpendicular, that actually decreases. Notice how the blue line decreases from there to there to there. Okay? Hence, as the angle increases, the perpendicular component of the force due to gravity decreases, just like we said. The normal force is directly proportional to the perpendicular component of the force due to gravity. So that normal force is equal to that normal force, that's equal to that, that is equal to that. But because all of these perpendicular ones decrease as the angle increases, the normal forces also decrease. Okay? Another thing that we need to know is the force of friction is directly proportional to the normal force. Since these normal forces decreased, the forces of friction must also decrease from A to B to C. So therefore, what we can say is, as the angle of the incline increases, the kinetic friction decreases. So when we go from A to B to C, the friction decreases. So we can now make our claim. We said that as the angle increased, the force due to gravity in the the parallel direction increased, but the friction decreased. So if we combine those forces together, that means overall the acceleration should increase because that value is increasing while that value is decreasing. Our claim is, since the parallel component of the force due to gravity increases as the angle increases, and since the frictional force decreases as the angle increases, the acceleration increases as the angle increases.